Okay, so now we're going to derive some expression. This is an expression you would have seen in your undergrad class, relative velocity of 2 points on a rotating rigid body. Okay, so imagine we have some base frame as usual, and we have some rigid body. Um, and we have a couple of points on the rigid body. And this rigid body has angular velocity omega with respect to this frame O or 0. Okay, rigid body B has angular velocity omega relative to frame 0. Let's ask the question first and then let us answer it. What is V Q with respect to P in frame 0? Okay, what is Q with respect to P? Okay, so first of all, we realize that VQ with respect to P is d by dt of V R Q with respect to P. Okay, the position vector from P to Q. And recall that if we had a vector, well, first of all, let's say RQ with respect to P is fixed, or it's a constant in body B. And we just derived this relationship, recall, for any vector G fixed in B, dg by dt equals omega cross G. Okay, so that's it really. So RQ with respect to P is one such vector. So therefore, VQ with respect to P equals, well, d by dt of RQ with respect to P equals omega crossed with RQ with respect to P. Okay, so let's just box that thing. VQ with respect to P equals omega cross RQ with respect to P. This is the relative velocity of Q and P with respect to P where Q and P are 2 points on a rigid body. Okay. And one could, of course, write this in perhaps the more familiar form, um, which is the version you may have seen in your undergrad classes, uh, perhaps in a 2D context, is this. Okay, so you may have seen either this version or this version in a previous lecture. Okay, so this is again a relationship we are going to use over and over again as we are doing rigid body dynamics, which is the velocity of the relative velocity of 2 points on a rigid body, or the velocity of 1 point on a rigid body given the velocity of another point on a rigid body and the angular velocity. So